Hello, I'm Kyungwoo, a software engineer working at Meta. I collaborated with Mamman, Sharon, and Alice on this project. The topic of my presentation today is practical global merge function with ThinLTO. So the mobile app size is steadily increasing as the more features are constantly added. The large apps, large and slow apps impact user experience and user retentions, which directly impacts our revenue. The graph below illustrates the growth of app size over the past year. As shown in the green line, the code size optimizations are critical to slow down this trend. In this presentation, my primary focus will be on function outlining and function merging, both of which are key components of size optimization. Function outliner basically identifies same code sequence that are repetitive and replace them by function calls. There are two outliners available in LLVM, IR outliner at IR level, opt level. The other one is machine outliner at codegen level. We noticed that the machine outliner is particularly useful in our target because more outlining opportunity appear after IRs are lowered down to machine IR level. So for the remainder of this presentation, I will assume the usage of a machine outliner as our function outliner. So here is a simple example. So let's say we have two functions. As you see, the code, the bottom part shown in green are identical, so they are repetitive. So if we outline them, we're going to replace such green code by the function call shown in red. So we ended up with having only 7 instructions in right-hand side as opposed to 8 instructions in left-hand side. So we basically save 1 instruction if we ignore the other metadata. So a function merger does a similar thing. The scope is actually the entire functions. Rather than specific code sequence within the block that machine outliner does. LLVM has already the built-in function merger, but we observed that the existing built-in function merger merge only identical functions, which is essentially the same as linker's identical code folding. So we are questioning about the effectiveness of built-in function merger. A function merger can also handle a similar code by parameterizing different constant. So in this example, given two functions, they look very similar except the core targets, so the global constants, f and f2, are only different. If we merge these two similar functions into a shared function, we need to introduce additional parameter here in x2. And then we provide a different context through the x2, like this. So the function merger and function outliner may appear very similar. However, they are actually distinct from each other. They can complement each other's operations. So let me compare these two things in this following context. So basically, the function merger operates at IR level, while the function outliner operates at machine IR level. As I said earlier, the scope of merger is for entire function, whereas the outliner is only specific sequence of code within the block. Function merger is able to not only identical but also similar code which is not the case with the function outliner. So why is that? This is due to the fact at the IL level, it is much easier to match a similar code using SSA, and also it's much flexible to manipulate IR to provide a different context. On the other hand, at machine IR level, in particular right after register allocation, it is difficult to basically use extra register to provide a different context through the parameters. On the flip side, at machine IR level, machine outliner is able to form a custom calling core whose overhead is very low. On the other hand, function merger must adhere to core API, whose overhead tends to be high. So overall, the function outliner makes a great impact on reducing binary size, which is not the case function merger. When it comes to debug metadata considerations, synthesizing entire function from the function merger while maintaining the debug data and other metadata is very challenging. On the other hand, the machine IR level, because function outliner operates at within the block level, so missing some debug information is not a big deal in practice because the actual core sites are still retained within the original block. So lastly, ThinLTO applicability. So when building large application, build time is critical, which is why we use the ThinLTO for mobile app build as opposed to full LTO. However, none of the existing methodology, function merge methodology, is applicable to ThinLTO. Is it because they requires explicit comparison of IRs, which is not available in ThinLTO context? Actually, same challenge already there for function outliner, but we actually develop a global outliner that can overcome this limitation to some degree. So in this presentation, actually, we would like to apply similar global approach for function merger applications. So now I'm going to show how we envision designing our global function merger. First, I want our global merger to work effectively in conjunction with function outliner and also linkers ICF. We basically we want function merger handles similar functions, while the majority of these similar functions was dealt by the function outliner. Second, we aim to ensure the function merger is scalable with the ThinLTO. To achieve this, we use a summary called the stable functions to track the similarity of the functions. As you know, in ThinLTO, each module runs in parallel independently. We have to create a unique instance of merging instance within each module's context. And also to prevent invalidating summary, we actually avoid directly modifying core sites while creating things all the time. This approach actually allows us for merging functions in any order. Finally, our design remains sound even in the presence of mismatches between IR and summary. So we aim to strive to maintain the integrity of the functions like the debug data and metadata as possible, which is critical in productions. So let me start with the high-level overview, ThinLTO overview first. So as you probably know already. So as you know, the input to the ThinLTO pipeline consists of multiple Bcode files whose summary was read by ThinLink. And then a global summary and decision was made into index, which includes some of the cross-module aligning candidate, the import list for cross-module aligning opportunity. However, the majority, the main build pipeline happens in opt and codegen, which runs in parallel. So the function merger actually located at the end of IR paths. Function outliner, basically machine outliner, is truly at the end of the codegen path. Finally, linker stitch these together into the final binary. Right? So let me just recap of how ThinLTO works with the global function outliner that has been published in compiler construction last year. So the key idea is repeat machine outliner using two codegen rounds framework. So basically, in first codegen round, we collect some local instance of outlining as usual. After that, we publish the stable hash of local outlining instance into the global prefix tree. During the second codegen, we use this global prefix tree information to identify cross-module outlining opportunity. And then finally, linker forced identical outline functions to achieve the binary size reductions. So let me give you a more concrete example. So let's say we have two functions defined in module 1 and another similar function defined in module 2. So they look very similar. So if we outline them, we only are able to outline within the module 1 because they are repetitive within module 1, but module 2, there are only one single instances, right? As a result of outlining, we compute stable hash for the outlined function, in this case y and b, for instance. And then we publish such a sequence into global prefix tree. And during the second codegen, we start from the scratch. At this time, same as in the first case, we outline the local instances. But now we have a global prefix tree that was published in previous step. Now we use them to match another instance in module 2, so we can outline cross-module candidate optimistically. But it's worth noting that we create unique instance of outline functions because it independently operates within each module. Finally, at link time, if the outline functions are truly identical, they can be folded into single function. Right? So let me provide an overview of ThinLTO with the global function merger, which is the main topic of this presentation. So basically, we want to fit into the two codegen round framework, like global outliner. But the function merger was located in opt level. So the one we try to do is basically push down the function merger to the beginning of codegen, which is codegen hook. So now the rest of are very similar. So basically, we run codegen round twice. Basically, first codegen round analyzed functions to produce some summary. So we call the stable function. And then we publish into global merge info. During the second codegen, we merge stable functions optimistically using these global informations. So let me go into a little bit more detail. So what the stable functions are. So stable functions are summary, which is independent of IR, which is key because we need to make a decision out of the IR. Basically, it has a stable hash, which is represent the entire function, while ignoring some constants that we track. So basically, the constants like some specific operations like store or load or core instructions. The second part is we need to keep track of such locations of constant that we ignore. So we have to actually build these two informations. and then publish all this information into global state, global merge info. So global merge info is basically a map that groups all the stable functions that share the same stable hash key. So once everything is published, then we need to determine the minimal set of locations of constant that are different across the same stable functions. So that becomes actually a parameter. So let me give you a more concrete example. So let's say we have very similar functions across two modules, and there are three functions like this. So during the first codegen, we are not actually merging. We just analyze to produce summary information, which is stable functions. So in this case, we ended up with producing same hash because we ignore the constant, global constant, in this case F1, F2, F3. So we have the same hash Y, while we tracking the location of such constant. And then we published into the global map, merge information. Basically, it groups all the same stable function that have shared the same stable hash key, which is Y. And then we determine the minimal set of locations that need to be parameterized. So during the second codegen, using this information, we can optimistically create a merging instance within each module context. The key essential part for the correctness, within the module, each module, we have to explicitly compare IRs because there was a possibility of hash collisions, and maybe there's some corruption in summary. And then we also create unique merge functions for safety. And then Linker does a similar job, as I described earlier in Global Outliner. So continuing with the same example during the second codegen. So now we have a global merge info matching against the IR. And then, as I said, the decision was made individually within each module. So we create the unique outline, unique merge function within each module 1 and module 2. If they ended up with being the same identical function, they will be folded by linker, like this. So what if we enable both function merger and the global function merger and global function outliner? So design looks like this. You can actually using the same codegen, two codegen line framework, which actually produce two codegen artifact, global prefix tree, and the global merge informations. Okay. So let me give you an example. I mean, let me provide our evaluations. We basically evaluate two set of benchmarks compared with OZ, minimum size optimization, and ThinLTO. The first set is iOS mobile apps developed by our company, which are written in Objective-C and Swift. These mobile apps are relatively large, ranging from 50 megabyte through 200 megabyte in size. The second set is a spec CPU, which is well-known benchmark available to the public. This benchmark relatively small. I don't think they are representative at all of mobile apps, but I just evaluate them for comparison purpose. We've observed that there was some build time regressions because you will repeat codegen. They're ranging from 6 to 40% regressions. But fortunately, the large regressions, like 40%, happens on small benchmarks like a spec. Basically, the small regression only happens on the large benchmarks, a large program that we're aiming for. So overall build time is not that great deal in production, and because we are targeting large applications. There are several ways to avoid repeating codegen, but one way is to use codegen artifact produced from prior build for the subsequent build. We are actually exploring such opportunity. So this is code size saving. with outliner only, so without function merger. So local outlining is the default motion outliner case. So we saw code size saving from 6 to 11%. Once we enable global outliner, we actually more than double. So like 8 to 70% for the most iOS app that we target. So as you expect, the global outliner is more effective on the large program compared to small spec program. So this graph shows a comparison of code size improvement by varying different function mergers. Now I basically disable function outliner completely. So default function merger is built-in LLVM 1. As expected, it's not that effective because ICF already does the same job. The local merger is the one that we ported over from Swift pass function merger down to main LLVM LTO pass so that we can use it. This function merger also do some decent job, save up to 2% in our code base. Lastly, once we enable global merger, we can actually see up to almost 6% code size saving in some iOS app. So now let me demonstrate how these work together. Basically, this graph shows the code size saving by varying the different function mergers, same as before, but on top of the global outliner. So the effectiveness of function merger tends to be diminished, but still the global function merger still produce a significant of size improvement up to over 3.5%. We also observe that the global function merger has only marginal effect on the small spec CPU benchmark, except on that PP, I think. So to conclude, I will demonstrate I introduced the new global merger function and evaluate the effectiveness of the global merger functions. So as for the future work, we are currently exploring ways to avoid repeating codegen to improve the build time. As you know that now LLV is available for macOS, so it will be interesting in comparing LLD implementation versus LLD because LTO paths are slightly different in between these two. Finally, we are happy to upstream all of these changes, but I think it will take some time because we need to stage some changes. Also, with the help, of course, with the help of the communities and interest, maybe we can speed up this process. I think all right. I think that's it. Thank you for your attention. I'm happy to take any questions. Yes.
I'm supposed to use the microphone. Great talk and fascinating results. You talked about the size savings. There is a performance overhead to outlining particularly. Do you have a measure for how much the performance is slowed by outlining?
I don't present this performance number in this presentation, but I do have, previous my experience. Yes, if I remember correctly, of course, outlining impacts the performance significantly because it incurs a lot of core overhead. However, we do have a profile guide optimization in place in our production, so we can actually profile guided outlining in our case, so that we basically bail out all these code folding, outlining, such size optimization on the hard code, while we only aggressively applying code size optimization for only cold code. Does that answer your questions, or your questions about how much regressions?
I was just curious.
Yeah, which is going to be very slow. If you apply outlining blindly, all the CPU bound cases, the slowdown is going to be up to 2x, 3x. You say it's going to be a huge number. But if it's IO bound, especially for mobile app, such a CPU slowdown is not a big deal because program is already slowed down from the IO, like waiting for network, waiting for devices. So that's why mobile apps are typically optimized for size, no matter what, in many cases. I'm not saying we 100% do that, but in certain cases, most of cases, we mostly optimize for size in mobile applications. Okay?
So we experimented with different function mergers, even some of the past implementations of the global function merging. There's a couple of papers that were published in the past.
Yeah.
And when we played with all those, two common issues we saw. One is that most of them weren't really robust when it comes to attributes. Like whenever someone would add new attribute to LLVM, they would often break. And the other issue was dealing with debug info. Usually they would produce completely garbage or incomplete debug info. So have you encountered any of this in your work? Is this something that you're dealing with in any way?
Yeah, actually, so actually we evaluate the one of work published from University of Edinburgh. I think we actually evaluate that. There are actually two major issues that we faces. One of them is so basically, they do. Although their approach is very aggressive, they can even sequence alignment, and so that they can merge very dissimilar functions. However, they need to, as I already described in our talk, we have to implement, maintain the integrity of the function. So basically, they have to come up with the synthesize the entire function or entire block by introducing extra fee node, etc. While not maintaining metadata and debug data. So basically, when we actually apply their approaches, it actually crashes when we build the app. Swift, Objective-C, they need to maintain all such of metadata. So and also, the second issue is, is a secondary, but their cost model basically. They don't actually consider, testing their evaluations against the machine outliner because outliner already handles the, common code pattern that can be easily outlined. So it's very questionable whether that's be applicable to the mobile app that we are aiming for. Yeah, so that's why we trying to, kind of balance these two words. So function merger handle only subset of similar function. So we basically replace only the constant. So we are not actually creating new function body. We basically try to maintain the existing function body. So that means we are not deleting debug information at all. We only replace the operand constant by, basically constant by parameters. However, as you can imagine, ICF or false. So you can avoid this optimization issue, like in debugging issue in optimized binary, right? So if you can fold these two in the single binary, and basically single binary cannot pointing to two different source locations at all. So that means we only preserve only one of them. So this is how we live. So because the limitation of dwarf and any debug informations, we are not able to map single binary location to multiple location. But we're actually thinking about other approach like maybe extra metadata or through the UI or representation. We may provide assist, more debug information. But as of today, I don't believe the existing debug information provide the different source locations on the single binary location. So this is how we live. So.
Okay, thank you.
Okay.